Pre-training starts with raw text before any task-specific tuning. The main goal here is to build the training loop, measure how well the model predicts text, and get the model ready for later fine-tuning. These are the pieces that make pre-training work end-to-end: evaluation, training, saving progress, and reusing pre-trained weights. Loss values tell us whether the language model is getting better at predicting the next token. Tracking both training and validation loss also shows whether the model is learning general patterns or just memorizing the data. The training function ties the whole model together: forward pass, loss calculation, backpropagation, and parameter updates. Once that loop is in place, the model can actually learn from the unlabeled text. Saving weights lets training resume later instead of starting over. Loading them back also makes it possible to continue training from a model state that already knows useful language patterns. Pre-trained weights can give the model a strong starting point, so fine-tuning begins from a learned representation instead of random initialization. That usually means faster convergence and better results on the downstream task. The architecture is already in place, so the next step is to make it train well and to measure whether the generated text is improving. From there, saving and loading weights becomes practical, and pre-trained weights can be used as a head start for later adaptation. The figure divides the project into 3 stages, and the important part here is stage 2. That stage contains the training code, the evaluation step, and the save and load workflow that turns the model into something you can keep improving. This roadmap shows where the current work sits in the full build. Stage 2 is the bridge between a working architecture and a usable language model, because it adds learning and persistence. The trainable numbers inside the network are what learning actually changes. Once that idea is clear, it becomes easier to understand how PyTorch stores them and how the optimizer updates them during training. In a neural network, the weights control how inputs are transformed, so adjusting them is the core of learning. PyTorch keeps those values inside modules like linear layers, and it also gives access to all trainable parameters at once, which is exactly what the training loop and optimizer need. Evaluating a text generator starts with a simple question: How close is the model's next token prediction to the target text? That answer gives us a way to measure progress before and during training. The path here is straightforward. Rebuild the generation setup from Chapter 4, generate some text, and then turn that output into a numerical score. Once that score is in place, training and validation losses tell us whether the model is improving. The first part of the diagram marks the generation setup, then the evaluation step, and then the training and validation losses. Those are the three pieces we need before we can talk about training the model itself. That roadmap is important because it shows the order of the work. First produce tokens, then score them, then use that score to guide training. Each step depends on the one before it. A GPT model produces text by taking token IDs as input and predicting the next token repeatedly. Before any evaluation makes sense, we need that generation loop working. The model is created with the same architecture settings as before, except for one practical change that makes the example easier to run. The point is to have a real GPT instance ready for generation and later for evaluation. The context length is shortened to 256, so the model is cheaper to run during training and evaluation. Dropout is set to 0 here because the model is being used in evaluation mode, so we want deterministic behavior rather than random noise. Reducing the context window is a practical move for experimentation. It lowers the compute cost immediately, and the later pre-trained model can still be restored to a longer context size. The only real change from the previous chapter is the smaller context length. That keeps the model light enough to train on ordinary hardware while still using the same basic architecture. The original GPT-2 configuration handled 1,024 tokens, and that larger setting comes back once pre-trained weights are loaded. For now, the smaller context is a compromise that makes the workflow practical. Generation depends on moving back and forth between human text and token IDs. Those helper functions make that conversion reusable, which matters throughout the rest of the chapter. The important part of the diagram is the cycle. Text goes into the tokenizer. Token IDs go through the model, and the model's logits are turned back into token IDs and decoded into text. That round trip is the core mechanism behind generation. Generation is really a three-step translation process. The model never works directly with words. It works with token IDs, and the tokenizer handles the conversions at the ends. First, the tokenizer encodes the prompt. Then the model produces logits for the next token, and those logits are mapped back into token IDs before decoding gives readable text again. The code that follows wraps those conversions into small helpers, so the generation function can work with the right representation at each stage. That separation keeps the process clear and reusable. These helpers bridge the gap between text and tensor form. Once they exist, the model can accept prompts and return readable output without extra conversion code every time. The first helper adds the batch dimension, because the model expects a batch even when there is only one prompt. The second helper removes that extra dimension, so the token IDs can be decoded back into normal text after generation. Those two shape adjustments are small, but they keep the model interface consistent. Without them, the tokenizer and the GPT model would not agree on the tensor shape. A trained language model should extend the prompt with sensible language, but an untrained one usually cannot do that yet. The next output makes that limitation very visible. The continuation is noisy and fragments of words appear without structure. That tells us the model is sampling from a random set of weights rather than from a learned language distribution. Coherence is what we need to measure, but it cannot be judged by intuition alone. A numerical loss lets us compare outputs consistently and track whether training is making the model better. The loss becomes the score we watch during training. Lower values mean the model is placing more probability on the correct next tokens, which is exactly the direction we want. The next step is turning prediction quality into a number. That number gives the training loop a target to improve. The loss calculation follows the same logic as next token prediction. Compare what the model assigns high probability to against the true next token. A small worked example makes that logic easier to see before we scale up to full data sets. The generation function hides a sequence of small operations that we need to understand before evaluating the model. Those same tensor steps will later feed directly into the loss calculation. The left side starts with tokenized input, The middle produces probability vectors over the vocabulary, and the right side selects the most likely token IDs and turns them back into text. That chain is exactly what we need to score against the targets. The figure uses a tiny vocabulary, so the steps fit on the page, but the structure is the same for a full GPT model. The only difference in practice is that the vocabulary is much larger. A toy figure may show only 7 tokens, but the real model predicts over 50,000 possibilities at each position. That larger vocabulary is what makes the probability vectors so wide in the actual code. The example code uses 2 prompts, so the batch behavior becomes clear. That lets us see the same computation repeated across multiple rows, not just one sentence. These inputs are the token ID version of the prompts, which means the model can process them directly. From there, the next token prediction problem becomes a tensor operation. Each row is one input example, and each number is a token ID. The important idea is that the model sees batches of token sequences, not raw strings. The target tensor contains the tokens we want the model to predict one step later. That shift is what turns language modeling into a next token classification problem. Notice the one position shift. Each target token is the next token after the input token in the same row. That alignment is what the loss function will compare against the model's predictions. That shift is the core training signal. At every position, the model learns to guess the next token that should follow the current one. Once the input batch goes through the model, we get logits for every token position. Softmax turns those raw scores into probabilities over the vocabulary. Gradient tracking is turned off because no learning step happens yet. The softmax runs across the vocabulary dimension, so every token position gets a full probability distribution. These comments mark the 2 ideas that matter most. We are only evaluating, and each output vector contains 1 probability per vocabulary item. That shape tells us the model is predicting across the full vocabulary at every position. The tensor shape confirms the structure of the batch. 2 examples, 3 token positions each, and a probability distribution over the whole vocabulary at every position. That shape means the model has a probability vector for each token in each example. The last dimension is the vocabulary size, which is why it is so large. The first dimension is the batch size, the second is the number of token positions, and the last is the vocabulary. From there, the generation function can choose the most likely next token at each position. Argmax collapses each probability vector to a single token ID by selecting the largest value. That gives the model's most likely next token choice at each position. The argmax runs across the vocabulary dimension, so every position keeps just one winning token ID. Keeping the extra dimension makes the result line up with the original batch structure. Each input row produces its own sequence of predicted token IDs. That mirrors the original batch shape, only with the vocabulary dimension removed. The first block belongs to the first example, and the second block belongs to the second example. Those IDs are the model's best guesses, even though the model has not learned anything useful yet. Those labels simply separate the two examples in the batch. They make it easier to compare each prediction sequence to its corresponding target sequence. After prediction, the final step is decoding. That lets us compare the model's output in a human-readable form against the target text. This comparison exposes the gap between the desired continuation and the model's guess. Decoding both sequences makes the mismatch easy to inspect directly. The decoded output does not resemble the target continuation at all. That difference is what the loss function needs to measure numerically. The target text is a normal continuation, but the model output is a jumble of unrelated tokens. That contrast is exactly why training has to happen before the generator becomes useful. A random continuation tells us the model has no learned structure yet. The next task is to convert that mismatch into a loss value that training can reduce. The diagram shifts from generation to evaluation. Now the goal is not to pick a next token, but to score how close the predictions are to the target tokens. That score becomes the training signal. This marks the move from producing text to measuring it. Once we can score predictions, the same number can drive weight updates during training. Loss captures distance in a probabilistic sense. Smaller distance means the model is assigning more of its probability mass to the correct next tokens. Training works by raising the probability at the positions that correspond to the correct targets. When those positions get higher scores, the model is closer to predicting the right next token. Focus on the highlighted target positions in the probability vectors. Training tries to push those particular entries upward, while other entries fall relatively lower. Before training, the probability vectors are mostly random. The goal is to reshape them so the correct token IDs become the strongest entries. With such a large vocabulary, untrained probabilities are tiny and spread out. That is why even the right token starts with a very low score before learning begins. To measure quality, we need the probability assigned to the correct token at each position. That gives us the exact values the loss will use. This indexing pulls out the probability of the correct token at each position for each example. Those are the only probabilities that matter for the loss calculation. Each batch gives 3 values because each input sequence has 3 token positions. Those values tell us how confident the model was at each step. These numbers are extremely small, which is what we expect from an untrained model with a huge vocabulary. The right token is barely preferred over all the alternatives. The training objective is to make the correct token more likely than the others at each position. In language modeling, that means the model learns to choose the next word that actually belongs there. The way those probabilities improve is through backpropagation. A loss value tells the optimizer how to adjust the weights so the correct token scores rise. Backpropagation uses the loss to push the model in the right direction. The network parameters change, so future predictions place more mass on the targets we want. A loss function compares predicted output with desired output and turns that difference into a single number. That number is what the training algorithm tries to reduce. The next step is to work with log probabilities, which makes the optimization behave more smoothly. After that, averaging and sign changes turn the result into a standard loss value. Concatenating the target probabilities gives one list of correct token scores, and the logarithm turns each tiny probability into a negative log value. Those negative values are easier to aggregate into a loss. The figure shows the full loss pipeline: probability selection, logarithm, averaging, and sign flip. Those steps compress many token-level predictions into one training score. The loss is not a single mysterious formula. It is a sequence of simple operations. Once those operations are clear, the built-in PyTorch version becomes much easier to trust. After the log transform, the values are all negative because the original probabilities were less than 1. More negative values mean the model was less confident in the correct token. These numbers are the log probabilities for the correct tokens across both examples. They're negative because the original probabilities were small. Working in log space is standard in optimization because it turns products into sums and gives smoother numerical behavior. The detailed reasoning is beyond this chapter, but the practical effect matters here. Averaging turns several token-level scores into one score for the whole batch. That gives a compact measure of how well the model handled the example sequence. Taking the mean combines all the token-level log probabilities into one number. That single value is the batch-level estimate of how well the model matched the targets. This average summarizes the batch in one value. Higher values are better here, but deep learning usually flips the sign, so the loss is minimized instead. The average is still negative because these are log probabilities. The training objective will turn that into a positive loss that the optimizer can minimize. Training usually minimizes the negative of the average log probability. That simple sign flip gives the loss its standard form and makes smaller values better. Multiplying by -1 turns the score into a positive loss. That is the form the optimizer expects when it searches for weights that improve prediction. That positive value is the cross-entropy loss. PyTorch provides it directly, so we do not need to build the whole sequence of operations by hand every time. Cross-entropy compares what the model predicts with what the data says should happen. In language modeling, it is the standard way to score next token predictions. The true labels and the predicted probabilities are treated as distributions. Cross-entropy tells us how far apart those distributions are, token by token. For discrete tokens, PyTorch's cross-entropy is effectively the same quantity we just computed manually. That is why the two terms are often used almost interchangeably in practice. Before calling the built-in loss, the shapes need to match what PyTorch expects. The logits and targets carry different dimensions, so we flatten them first. Printing the shapes makes the dimensionality clear before we reshape anything. That check prevents mistakes when the loss function receives batch sequences. The printout confirms the mismatch in rank. Logits carry the vocabulary dimension, while targets only carry the token IDs. That difference is normal and expected. Logits have one extra dimension because every token position predicts across the full vocabulary. Targets only store the correct token ID for each position. That is the key shape difference. The loss function needs one row of vocabulary scores for each target token, which is why the tensors must be reshaped first. Flattening combines the batch and token axes, so every prediction becomes one row. That matches the input format expected by PyTorch's cross-entropy function. Flattening the first two dimensions of logits turns the batch into a simple list of prediction rows. The targets are flattened into the same number of labels, so each row and label pair lines up correctly. After flattening, each token position is treated as its own training example. That is exactly the layout cross-entropy expects. Now there are 6 prediction rows and 6 target IDs. That one-to-one alignment is what makes the loss calculation work cleanly. Targets hold the correct IDs, and logits are the unnormalized scores before softmax. The loss compares the two after the tensors have been reshaped into matching forms. The built-in function bundles the manual steps into one call. It applies the normalization, picks out the target positions, and computes the loss in a single operation. With the flattened tensors in place, the loss call becomes very short. PyTorch does the probability transform and target comparison internally. The results should agree with the value computed step by step earlier. That match confirms the built-in function is doing the same work. The value matches the earlier hand calculation exactly. That tells us the built-in cross-entropy is a reliable shortcut for the same loss. Perplexity is another way to read the same loss value. It often feels easier to interpret because it can be thought of as the model's effective uncertainty over the vocabulary. Like cross-entropy, perplexity measures how well the predicted distribution matches the true next token. Lower perplexity means the model is less confused. Perplexity tracks the same trend as loss, just on a different scale. When a model improves, both loss and perplexity go down. Perplexity is computed by exponentiating the loss. That converts the log scale score back into a more intuitive count-like measure. A perplexity value can be read as the model acting uncertain among that many choices. In this example, the model is effectively spreading attention across tens of thousands of tokens. The small example shows the mechanics clearly, but the real evaluation needs the whole dataset. That is where training and validation losses become useful across many batches. Now, the same loss computation is scaled up to the dataset level. That gives us one score for training data and one score for validation data. The idea is to measure loss on both splits so we can see how the model behaves on data it learned from and data it has not seen. That comparison is central to judging generalization. The split into training and validation is the first thing to track, then the tokenization and chunking into fixed-length sequences, and finally the batching step. Those steps prepare the data for the loss calculation. Once the dataset is prepared, the same cross-entropy logic can be applied across the full training and validation sets. That turns a single example calculation into a training metric. A public domain story keeps the example simple and legally clean, and the small size makes the code fast enough to run on modest hardware. The goal here is pedagogy, not scale. The same pipeline can scale to a much larger corpus if needed. The book's code base includes that option for readers who want a bigger training setup. Pre-training a large language model takes serious compute. The numbers behind a modern model help explain why these small examples use compact datasets and short contexts. A 7 billion parameter model can require hundreds of thousands of GPU hours and very expensive hardware. That scale makes the cost of large model training very concrete. The next code block reads the text file into a string. From there, we can count characters, tokenize it, and split it for training. This simply opens the story file and reads the entire contents into memory. Once the text is loaded, the rest of the pre-processing steps can work on that string. Before splitting the dataset, it helps to see its size in both characters and tokens. Token count is the more relevant number for model training. The character count gives a rough sense of text length, while the token count tells us how many model steps the story contains. Token count is what matters for batching and context windows. The result shows a short story by modern dataset standards, but still enough to demonstrate the full pre-processing pipeline. That small size is what keeps the example manageable. There are far fewer tokens than characters because tokens can cover pieces of words and punctuation. For training, that token count is the number we care about. That amount is small for real pre-training, but it is perfect for a quick classroom example. The model can run end-to-end, and pre-trained weights can be added later if needed. The text is split into a training portion and a validation portion, then chunked into fixed-length sequences for batching. The small figure uses a short chunk length, but the actual loader uses the full context length supported by the model. Track the split first, then the tokenization, then the chunking into fixed-length pieces, and finally the shuffle batches. Those are the exact data loader steps that feed training. The figure shows the full pre-processing chain from raw text to batches. That chain is what makes the training and validation loss calculation possible. Using same-length chunks keeps the code simple and efficient. In practice, variable length examples can help the model handle a wider range of input lengths. A simple split ratio gives most of the data to training and keeps a separate slice for evaluation. That validation slice is what tells us whether the model is generalizing. The split point is computed from the chosen ratio, and then the text is sliced into two parts. That keeps training and validation data separate from the start. With the two text subsets ready, the data loader can turn each one into batches of token sequences. The same loader pattern from Chapter 2 handles both splits. The training loader shuffles and drops incomplete batches, so the optimization loop stays clean. The validation loader keeps order and keeps all available batches, because evaluation should reflect the full held-out split. A batch size of 2 keeps the example lightweight. Real LLM training often uses much larger batches, but the principle is the same. A quick pass through the loaders confirms that the shapes are what we expect. That sanity check is worth doing before computing losses. Printing the batch shapes verifies that inputs and targets are paired correctly. If the loader is right, both tensors should share the same batch and sequence dimensions. The output tells us how many batches each split produces and whether the dimensions match the chosen context length. That is a useful checkpoint before training starts. The training split produces several batches, while the validation split produces just one in this small setup. Every batch has matching input and target shapes, which is exactly what the loss function needs. That output confirms the split and the chosen batch size. The targets match the inputs in shape because they are shifted copies of the same token sequences. The next utility computes loss for one batch at a time. Once that works, the loader level loss becomes just an average over many batches. The batch is moved to the same device as the model, then passed through the network, and finally flattened for cross-entropy. This function is the core unit that turns one input batch into one loss value. Moving the batch to the same device as the model avoids device mismatch errors. It also lets the code run on a GPU without changing the training logic. A single batch loss function gives us a reusable building block. The loader level function can call it repeatedly and average the results across the dataset. Now the same loss idea is lifted from one batch to all batches in a loader. That gives a stable estimate for both training and validation sets. This function loops over the loader, accumulates each batch loss, and then divides by the number of batches to get an average. The optional batch limit is useful when a quick evaluation is enough during training. Those comments describe the control flow. The function can score the full loader or just a subset of batches if speed matters more than exactness in a given moment. The average gives a single number for the loader, while the optional limit lets training run faster when full evaluation is too expensive. That trade-off is common in practice. With the helper in place, we can evaluate both splits in one pass. The only remaining requirement is that the model and data live on the same device. The model moves to GPU if one is available, and gradients stay off because we are only measuring loss here. Then the same helper is applied to the training and validation loaders to get two comparable numbers. These notes highlight the important mechanics. Data and model must share a device, and evaluation should not build a backward graph. That keeps the calculation efficient. Once the loaders are evaluated, the two numbers tell us how the model performs on seen and unseen text. Those values are the baseline we will try to reduce with training. Both losses are high because the model has not learned the dataset yet. Near-identical training and validation loss is expected at this stage, since the weights are still random. A good model drives loss towards zero by predicting the next token accurately. These values are just the starting point before training changes the weights. Once training begins, the goal is to push this score downward. That improvement is what we will watch as the model learns to generate better text. The final diagram brings the sequence together: generation, evaluation, and then training. The loss computed here becomes the signal used in the next stage. The chapter now has all the pieces needed to start training. First, we generate text, then we evaluate it, and then we use that evaluation to drive pre-training. The next step is to train the LLM so the loss comes down and the text gets better. After that, alternative generation strategies and saving pre-trained weights become useful additions. Training an LLM means turning the model's predictions into a learning signal, then repeating that update many times until the weights improve. The core idea here is a simple pre-training loop that is easy to follow and mirrors how PyTorch models are usually trained. A clean loop makes the mechanics easier to understand before adding extra tricks. The goal is to keep the code short enough that the role of each step stays visible. Those techniques help with stability and learning rate scheduling, but they are not required to understand the basic training process. Leaving them out for now keeps the main loop focused on loss, gradients, and parameter updates. The important structure in this diagram is the cycle. Run through batches, compute a loss, form gradients, update weights, then repeat across epochs. The monitoring steps at the end matter too, because they tell us whether the model is actually improving while training continues. A training loop in PyTorch is really an organized sequence of the same few operations. Once that sequence is clear, the code becomes much easier to read because every line has a specific job in the learning cycle. The flowchart breaks training into 8 practical steps, from iterating over epochs to checking losses and samples. That last monitoring part is important because loss numbers alone do not tell the whole story about model quality. If any of the PyTorch mechanics feel unfamiliar, those earlier sections fill in the missing pieces. The loop still makes sense without them, but the supporting details become easier once the basic API is comfortable. That full workflow can be written as one function that handles training, evaluation, and sampling in a single place. Keeping it together helps the control flow stay explicit instead of scattered across many helpers. This function is the backbone of the training process. The important thing to watch is how it alternates between optimization steps and occasional checks on performance. The structure is straightforward. Initialize trackers, loop over epochs, loop over batches, clear old gradients, compute the loss, backpropagate, and step the optimizer. The evaluation check runs only at intervals, so training stays efficient while still giving us regular feedback, and the sample generation call at the end of each epoch shows what the model can actually produce. Each marker maps to one responsibility, and together they describe the whole training routine. The useful mental model is that optimization happens batch by batch, while evaluation and sampling happen only as checkpoints. Two helpers complete the loop. One measures progress numerically, and the other shows the model's actual text output. That combination is important because a low loss does not always mean the generated text is truly good. The evaluation helper switches the model into evaluation mode, so dropout behaves deterministically, then computes loss without storing gradients. That gives a cleaner measurement and avoids wasting memory on derivative tracking during inspection. The key line is the switch into eval mode before the loss is measured. Wrapping the loss calculation in no_grad keeps the pass lightweight, and then the final train call restores the model to its normal training behavior afterward. Those two choices matter for stable measurement. Dropout would add randomness, and gradient tracking would add overhead that we do not need when the model is only being checked. The sampling helper turns a short prompt into token IDs, feeds them through the model, and decodes the result back to text. That gives a concrete example of the model's behavior, which is often more revealing than the loss value alone. This helper temporarily switches to evaluation mode, encodes the prompt, generates new tokens, and then decodes them for printing. The final return to train mode is important because the main training loop needs the model back in its normal state afterward. Replacing line breaks with spaces keeps the sample readable in the console. That makes it easier to compare generated text across epochs without distracting formatting changes. The loss tells us how well the model predicts tokens on average, but the generated sample shows whether it can produce coherent language. Both views matter, because good training should improve the statistics and the actual text. AtomW is the optimizer choice here because it combines adaptive learning rates with a better form of weight decay. That usually gives cleaner regularization for large language models than plain Atom with traditional weight decay handling. Weight decay discourages the model from growing unnecessarily large weights, which helps reduce overfitting. AtomW applies that penalty in a way that works especially well for transformer training. Once the optimizer is set, the model can be trained with a fixed epoch count and regular evaluation intervals. The prompt at the end gives a starting point for sample generation so we can watch the text quality evolve. The seed keeps the run reproducible. The model is moved onto the chosen device, and AtomW is built from the trainable parameters. The training call ties everything together. It sets the epoch count, evaluation frequency, and starting prompt for the sample text. That call hands the optimizer every parameter that should be updated during learning. It is the standard way to tell PyTorch which weights belong to the model. This run is small enough to finish quickly on modest hardware, which makes the training behavior easy to inspect. The printed output lets us watch both the loss values and the generated text as learning progresses. The loss drops sharply, and the samples improve from punctuation stuffing to more grammatical language. At the same time, the validation loss stays much higher than the training loss, which tells us the model is learning the training set very well, but not generalizing equally well. The omitted lines are just more snapshots of the same trend. The important part is the pattern. Training loss keeps falling while the samples become more fluent. That change shows the model moving from rough token repetition to coherent continuation. Early on, it leans on commas and repeated words, and later it produces text that looks much closer to natural prose. The validation curve follows the same downward direction, but it levels off well above the training curve. That gap is a classic sign that the model is starting to memorize the small training corpus. A plot makes the gap between the two losses much easier to see than a table of numbers. It also helps connect the learning curve to the overfitting behavior that shows up in the samples. This plotting function draws both loss curves against epochs, then adds a second x-axis for tokens seen. The invisible line is a neat alignment trick because it lets the top axis match the same curve without changing what the plot displays. The second axis gives another way to read progress, since token count is often more informative than epoch count alone. The invisible plot is only there to make the tick marks line up correctly. When training loss keeps falling, but validation loss stalls, the model is fitting the training data too specifically. In a tiny corpus, that often leads to memorized text fragments rather than broad language skill. The curve to watch is the one where the two losses separate after the early epochs. That separation is the visual signature of overfitting, and it matches the memorized snippets we saw in the generated samples. The early drop means the model is learning useful patterns, but the later split shows that improvement is no longer carrying over to validation data. That is the point where extra training mostly sharpens memorization instead of generalization. That behavior is expected when the dataset is tiny and the model sees it repeatedly. On larger datasets, a single pass is often enough to learn useful structure without driving memorization so far. A much larger book collection gives the model more variety, so the same passage is less likely to be copied verbatim. That is why scale matters so much when training language models. The important part of this figure is the contrast between fluent continuation and copied training text. That contrast explains why a model can look successful on one metric and still need better generation methods. The model now produces language that reads smoothly, but some passages still come straight from the training set. The next challenge is to make generation more varied, so the output is less dependent on memorized text. At this point, the training function, evaluation, sampling, and basic optimization pieces are in place. The next step is to improve how text is generated and then move on to loading and saving pre-trained weights. Decoding controls how a model turns probabilities into words, and that choice changes both randomness and quality. The goal here is to move from plain greedy selection to methods that keep outputs varied without losing too much coherence. The first version of generation always picked the most likely token, so it was consistent but often repetitive. The two techniques on the board change that selection step in different ways. One reshapes the probabilities, and the other limits which tokens can even be chosen. Inference with a small model does not need a GPU, so the model can run on the CPU without much cost. Evaluation mode matters too, because it turns off training time randomness like dropout and gives stable predictions. The first line places the model on the CPU, and the second line tells it to behave like an inference model rather than a training model. That combination removes unnecessary randomness and prepares it for generation. The generation function feeds the current context into the model, asks for the next token, and repeats that step over and over. That token-by-token loop is the basic mechanism behind every decoding strategy we are about to modify. This call starts from a prompt and lets the model extend it for 25 new tokens. The important part is that the function uses the current context, so each new choice depends on the words already produced. The output shows what happens when a model follows only the most likely path. It is fluent at first, but it also drifts into a memorized passage rather than producing fresh text. That continuation is a clear example of greedy decoding. The model keeps choosing the highest probability next token, so the result is deterministic but not very original. Rerunning the same prompt would give the same continuation every time. Because the same largest score is chosen at each step, the same prompt leads to the same sequence again and again. That makes the process predictable, but it also limits variation and can lock the model into repeated phrasing. Temperature scaling changes how strongly the model prefers its top choices. By flattening or sharpening the probability distribution, it gives us a simple knob for making generation more random or more conservative. Argmax gives the single biggest option every time, which is why greedy decoding feels rigid. Sampling makes the model draw from the distribution instead, so lower probability words still have a chance to appear when the distribution allows it. A small vocabulary makes the mechanism easier to inspect because each token can be tracked by hand. With only a few candidates, the effect of probability scores becomes much more visible. This vocabulary maps each word to an integer ID, and the reverse map lets us turn an ID back into text. That reverse lookup will matter once we start sampling token IDs rather than words directly. The prompt fixes the current context, and a model now has to predict only the next token. Everything that follows depends on the logits assigned to the possible continuations of that phrase. These logits are raw scores before any normalization. Larger values mean the model is leaning more strongly toward those token IDs, but they're not probabilities yet. Softmax turns scores into a probability distribution, and argmax then chooses the most likely token from that distribution. The reverse vocabulary converts the chosen ID back into the word we can read. Softmax makes the scores comparable, and argmax finds the index of the biggest probability. Printing the reverse vocabulary entry turns that index into the predicted word. The largest logit sits in the fourth position, which is index 3 in Python. That is why the model picks forward under greedy decoding. Multinomial sampling still respects the probabilities, but it does not always choose the top one. Tokens with higher probability are selected more often, while smaller probabilities still keep a non-zero chance. The random seed makes the sampling reproducible for the demonstration, and multinomial draws one token according to the probability weights. Even with the same distribution, the draw can differ from Rmax because it is sampled, not selected outright. That is why the same most likely token can still be joined by other tokens over many draws. The highest probability word dominates, but it no longer has a monopoly on the output. This function repeats the same sampling process many times and counts how often each token appears. That gives a frequency view of the distribution instead of a single draw. A single sample can be misleading, so repeated sampling reveals the pattern more clearly. The counts should roughly match the probability mass assigned to each token. The counts confirm that forward is chosen most often, but not always. Other plausible tokens still appear, which is exactly the extra diversity sampling introduces. With multinomial sampling, the model can produce forward most of the time and still occasionally choose closer, inches, or toward. That variation makes generation less repetitive, but it also opens the door to weaker or less sensible continuations. Temperature changes how sharp the distribution is before sampling. Lower temperatures make the model more certain, while higher temperatures spread probability more evenly across the vocabulary. Dividing by temperature rescales the logits before softmax. When the temperature is small, the differences between logits matter more. When it is large, those differences get softened. A temperature above 1 spreads probability across more tokens, which increases variety. A temperature below 1 concentrates probability into the most likely tokens, which makes the model more conservative. The plot compares the same logits under 3 temperatures: normal, very sharp, and very flat. That makes the trade-off visible. One setting concentrates mass on the best token, while another spreads it across many options. The 3 curves represent the original distribution, a sharper version, and a flatter version. The point is not that one is always best, but that temperature directly controls confidence before sampling. The figure makes the effect concrete. Low temperature pushes the model toward one dominant token, and high temperature makes the choices more even. That change is what later lets us balance creativity against coherence. Track the three distributions across the same token set. The sharpest one puts most of the mass on forward, while the flattest one gives more room to the smaller candidates like toward and closer. A temperature of 1 leaves the logits unchanged before softmax. Dropping it to 0.1 makes the top token much more dominant, and raising it to 5 spreads probability across the rest of the vocabulary. Using temperature 1 does not really change the scores, because dividing by 1 leaves them alone. Sampling from that distribution still keeps randomness, but it does so with the model's original confidence levels. At very low temperature, multinomial sampling behaves almost like argmax, so the most likely token wins nearly every time. At high temperature, unlikely tokens show up more often, which can create interesting text but also odd output like pizza. The frequency experiment now becomes a useful check on intuition. Changing temperature should shift how often pizza appears, because the probability mass is being redistributed before sampling. A faster way to reason about pizza is to read its probability directly instead of simulating 1,000 draws. The sampling frequency should roughly match that probability, so the distribution already tells you most of what you need. Top case sampling adds another layer of control by limiting the candidate set before sampling happens. Instead of letting every token compete, it keeps only the K's strongest options and removes the rest. Temperature alone can make the distribution too wide, which is why strange tokens can slip in. Top case sampling is useful because it preserves variety while blocking the weakest candidates from entering the draw at all. The idea is simple. Filter out the low-scoring tokens, then sample from what remains. That keeps the model focused on plausible continuations while still allowing more than one path. Focus on the top 3 logits and the masked-out tokens. The important move is that every non-top K entry is pushed to negative infinity before softmax, so it cannot receive probability mass. With K set to 3, only the 3 largest logits survive. After masking, softmax assigns 0 probability to every other token, so sampling is restricted to a much smaller and safer set. That masking trick is the key step. Once a logit becomes negative infinity, softmax turns it into zero probability, which cleanly removes it from the sampling pool. The first step is to identify the strongest candidates. After that, the weaker logits can be masked away before any probability calculation happens. Torch top returns both the values and the positions of the largest logits. Those positions tell us which token IDs survive the filter, and the values give the cutoff for masking. The three selected logits are the strongest candidates for the next token. Their positions identify the corresponding words inside the vocabulary. The highest score belongs to index 3, followed by index 7 and index 0. Those are the only token IDs that remain in play after the top K filter. The where function lets us keep the strong logits and replace everything below the cutoff with negative infinity. That gives a clean way to enforce the top K boundary before softmax. The condition checks which logits fall below the smallest value among the top three. Those values get replaced by negative infinity, while the surviving logits stay unchanged. The comments match the three branches of the masking step. Only the top three logits survive unchanged, and the rest are excluded from sampling. After masking, the shape of the score vector stays the same, but many entries are no longer usable. Softmax will convert those excluded values into zeros. Only three positions remain finite here, which means only three tokens can be sampled. Every other entry has been removed from consideration by the mask. Once the weak tokens are masked out, softmax can turn the remaining logits into a smaller probability distribution. The probabilities now sum to 1 across just the surviving candidates. This step converts the masked logits into probabilities for the surviving tokens only. The zero entries stay zero because they were already pushed to negative infinity. The distribution is now concentrated entirely on the top three choices. That means sampling will stay diverse, but only within a controlled set of likely tokens. The probability mass is concentrated on indices 3, 7, and 0, while the others are exactly 0. That is the top K restriction working as intended. At this point, temperature scaling and multinomial sampling can run on the reduced distribution. The next step is to plug both ideas into the generation loop so the model can use them repeatedly. The generation function now needs to support both filtering and sampling. Once those pieces are added, the model can switch between greedy decoding and more varied decoding without changing the surrounding code. The old function is being upgraded rather than replaced. The new version keeps the same token-by-token loop, but it adds knobs for temperature, top K filtering, and early stopping. This listing brings the ideas together in one place. The important thing to watch is how the next token choice changes depending on whether temperature or top K is turned on. The loop still generates one token at a time, but now it can first mask with top K and then risk scale with temperature before sampling. If temperature is 0, the code falls back to argmax, which restores deterministic decoding. Those comments mark the decision points. The loop builds the sequence, top K trims the candidate set, temperature controls randomness, and the end of sequence checks stop generation when the model says the text is finished. Now the same prompt can produce a different kind of continuation because the decoder has more flexibility. The settings determine how much freedom the model gets when choosing each next token. The seed makes the example repeatable, while top K and temperature introduce controlled randomness. A moderate top K value keeps the model grounded, and a temperature above 1 opens up more variation in the continuation. The results should feel less like copied training text and more like a fresh continuation. That difference comes directly from sampling instead of always taking the single highest score. This output is far less repetitive than the greedy version, which shows that the decoder is no longer locked onto one memorized path. The trade-off is that the text is more varied, but also less polished. The earlier generation echoed a passage from the training data, while this one explores a different path. That contrast shows why decoding strategy matters. The model weights stay the same, but the output can change a lot. Different tasks want different decoding settings. Some applications need consistency and precision, while others benefit from more exploration and creative variation. Low temperature and small top K values usually help when correctness matters more than novelty. Higher values are useful when variety matters more, even if the text becomes less predictable. Deterministic generation means removing the random draw from the process. The question is which settings turn the decoder back into a fixed, repeatable choice at every step. Deterministic behavior comes from turning off sampling, so the model always follows the same highest-scoring token path. That means using greedy selection instead of multinomial draws, and keeping the randomness controls from changing the ranking. Saving model weights lets a trained network survive beyond one notebook run. The important idea here is persistence. Once training has taken time and compute, those learned parameters should be reusable later. Pre-training even a small language model takes enough compute that repeating it for every new session would be wasteful. Keeping the trained weights means the work is done once, and the model can be reused whenever needed. The workflow has two parts. First, store the learned parameters, then rebuild the same model structure and place those parameters back into it. That separation matters because the architecture and the learned weights are related, but they're not the same thing. The figure breaks the process into a clear checkpoint. Training ends, the model is inspected, and the saved weights become the handoff point for later use or continued training. Focus on the saving step because that is what makes the model portable. Once training has produced a useful model, storing it protects that work. The same save state can support later inference, or it can become the starting point for more training. PyTorch recommends saving the state_dict because it contains the learned parameters organized by layer. That keeps the file focused on the parts that actually change during training, which makes loading straightforward later. This line extracts the model's parameter dictionary and writes it to disk. The model itself is not being serialized as a full object here. Only the learned weights are stored in the file. The file name can be anything, but using a PyTorch style extension makes the purpose clear. It is just a convention, yet it helps keep model checkpoints easy to recognize. To use the save parameters, rebuild the model class first so the layer shapes match. Then the stored weights can be copied into that fresh instance. The first line creates the same GPT model structure again, and the second line loads the saved weights onto the current device. The final line switches the network into evaluation mode, which matters because inference should not behave like training. Dropout is useful during training because it forces the network to generalize, but that randomness should stop when you want stable predictions. If training will continue later, saving the optimizer state is also worth doing so the update process resumes smoothly. Adaptive optimizers, such as AtomW, carry their own memory about past gradients and parameter updates. If that memory is lost, training restarts with a blank slate, which can hurt convergence and the quality of the generated text. This checkpoint saves two dictionaries together, one for the network weights and one for the optimizer's internal state. Storing them in a single file makes it easy to resume training from the exact point where it stopped. Restoring starts by reading the checkpoint back from disk, then rebuilding the model so the parameter names line up. After that, the optimizer is recreated and given its saved state, so training behavior continues consistently. The checkpoint is read first. Then the model is recreated and filled with the saved weights. After the optimizer is rebuilt, its saved state is loaded too, and model.train turns training behavior back on so optimization can continue from the stored point. The practical test is to open a fresh session, restore both files, and keep training without losing progress. That confirms the save and load cycle is working the way it should. The goal is to prove that the save checkpoint is complete enough to continue training cleanly. If the model and optimizer restore correctly, one more epoch should pick up from the stored state instead of starting over. OpenAI's released GPT-2 weights let us reuse a trained language model instead of rebuilding one from scratch. The main job here is matching their stored tensors to our GPT model so the model can generate text right away. That earlier model was useful because it kept the mechanics simple and the compute costs low. Now the same ideas carry over to a real pre-trained model, so the lessons shift from training from scratch to reusing learned parameters. That changes the economics completely. The hard work of learning language structure is already done. The weights are the learned numbers inside layers like linear layers and embeddings, and loading them gives us a model ready for generation and later fine-tuning. The original GPT-2 files were saved in TensorFlow format, so that library has to be available before Python can read them. TQDM is just a progress indicator, but it makes a large download much easier to follow. These dependencies have to be in place before the download, and loading code will run cleanly. Once they're installed, the rest of the process is just fetching files and mapping their contents into our model structure. The command installs the TensorFlow version needed to read the pre-trained files and the TQDM package for the progress display. The version bounds matter because loading code can break if the library interface changes too much. The download logic itself is mostly setup code, so it is cleaner to reuse a helper module from the repository. That keeps attention on the model loading steps rather than on boilerplate for HTTP requests. This code downloads the helper file directly from the online repository and saves it into the current Python directory. The key idea is simple. Fetch the module once, then import its loading function locally. A quick check saves time later because it confirms the file arrived intact and actually contains Python code. When code comes from the internet, a brief inspection is a sensible safety step. The helper function does two useful things at once. It returns the architecture settings and the actual pre-trained parameters. That separation matters because the model shape and the learned tensors have to match before anything can be loaded. This call asks for the 124M GPT-2 model and stores the return configuration in one dictionary and the weights in another. Those two objects are the bridge between OpenAI's save model and our own implementation. The pre-trained model is not one file. It is a small bundle of configuration, vocabulary, and checkpoint data. Seeing all 7 files confirms that the full model package was retrieved rather than just a partial download. These files cover the model setup, the vocabulary encoding, and the actual checkpoint tensors. The large checkpoint file holds the learned numbers, while the smaller files describe how to interpret them. Network problems and upstream changes are the usual causes when a pre-trained download does not work. In that case, the repository instructions are the right fallback because they are more likely to reflect the current file locations. Once the files are loaded, the next check is structural. Confirm that the configuration and weight dictionaries contain the expected contents. That tells us whether the loader understood the OpenAI format correctly. Printing the configuration and just the parameter keys give the compact sanity check. The keys show the major pieces of the model without flooding the screen with huge tensors. The results should show a small set of architecture values and a handful of top-level parameter groups. That is enough to verify that the checkpoint was interpreted in the expected format. These settings match the small GPT-2 architecture: vocabulary size, context length, embedding width, attention heads, and transformer layers. The parameter groups line up with the model parts we need to fill: blocks, layer norm terms, and the token and position embeddings. That distinction is important. Settings describe the shape of the network, while params contain the actual train values. We can inspect individual tensors when needed, but the full dictionary would be too large to read comfortably on screen. This prints the token embedding matrix directly and then checks its size. The shape is the critical detail because it tells us how many vocabulary entries are mapped into each embedding vector. The embedding table contains one learned vector per token in the vocabulary. Those vectors are the model's starting representation of text before any transformer block processes it. The matrix is large because it contains a vector for every token in the vocabulary, and each vector has 768 components. That shape confirms the model uses the expected embedding width for the 124M configuration. The smaller and larger GPT-2 variants share the same overall blueprint. What changes is how wide the embeddings are and how many times the repeated transformer parts appear, so the same loading code can still work across model sizes. The figure compares the GPT-2 family side by side. Track the repeated transformer blocks and the embedding width, because those two values are what change from one model size to another. The diagram makes the scaling pattern explicit. More parameters come from more repeated blocks and larger hidden dimensions. The computation stays the same, only the scale changes. Before copying weights into our model, the configuration has to match the pre-trained architecture exactly. That means selecting the right layer count, head count, and embedding size for the model variant we want. This table records the architectural differences between the GPT-2 variants. The important pattern is that bigger models use wider embeddings and more transformer layers and heads, but the general structure stays the same. For the smallest model, the existing 124M configuration already gives a good base. Updating it with the model-specific values is safer than rebuilding a new dictionary by hand, because fewer details can get lost. This code selects the small GPT-2 variant and merges its dimensions into the earlier configuration. Copying first avoids mutating the original settings, which keeps the base config available for comparison later. The context length also has to match the pre-trained model, because attention layers are built around that maximum sequence size. Our earlier 256 token setup is too small for these weights, so the configuration must be expanded. This single update aligns the model with the original GPT-2 training setup. Without it, the positional embeddings and attention window would not match the pre-trained weights. OpenAI included bias terms in the query, key, and value projections, even though newer LLMs often leave them out. Compatibility matters more than preference here, because the pre-trained tensors must fit the layer definitions exactly. Enabling this flag makes the attention layers line up with a pre-trained checkpoint. It is a small detail, but small details like this decide whether weight loading works cleanly. With the architecture settings corrected, the model can be built in the right shape. At this point, the network is still randomly initialized, so the next step is to overwrite those random values with the pre-trained ones. This creates the model and switches it into evaluation mode. Evaluation mode is the right setting for generation because we are not training and we want the layers to behave deterministically. The model now has the correct structure, but the values inside are still random. Loading pre-trained weights means walking through each matching layer and replacing those random tensors with the learned tensors from OpenAI. This helper checks that the source and destination tensors have the same shape before anything is copied. If the shapes disagree, it stops immediately. If they match, it wraps the loaded values as trainable PyTorch parameters. The loading function is where the two naming schemes meet. It takes the tensors from the OpenAI checkpoint and places them into the corresponding spots in our implementation. The full loader is mostly a systematic translation between OpenAI's parameter names and ours. The real idea is consistency. Every tensor has to land in the exact layer that expects it. The first assignments copy the positional and token embeddings. Then the loop walks through each transformer block, splitting the combined query key value tensor into 3 parts, mapping attention weights and biases, loading the feed-forward layers, and finishing with the layer norms and output head. Those notes explain the structure of the loader. The split is needed because OpenAI stores query, key, and value together, and weight tying at the output head reuses the token embedding matrix to say parameters. A concrete example helps. OpenAI's output projection tensor for the first block has one naming convention, and our model uses another. The loader succeeds by matching those two names to the same mathematical object. This kind of loader takes some care because the naming conventions are different and a wrong match can be hard to spot. Shape checking gives an early warning, and bad weight assignment would quickly show up as incoherent text generation. Once the tensors are copied into place, the model can be sent to the target device for inference. That prepares it for generation with the pre-trained values rather than the random initialization. The first line performs the actual parameter transfer, and the second line places the finished model on the chosen device. After that, the network is ready to run with OpenAI's learned weights. Generation is the best practical test of whether the loading process worked. If the weights are aligned correctly, the model should continue a prompt in a way that sounds internally consistent rather than random. This generation call fixes the random seed for reproducibility, converts the prompt into token IDs, and asks for a short continuation with sampling controls like top K and temperature. The context size comes from the pre-trained configuration, so the model can use the same window size it was built for. A sensible continuation is the sign that the loader, the architecture, and the weight mapping all agree. If the text reads smoothly, the pre-trained checkpoint has been transferred correctly. The generated continuation has the feel of a real language model rather than a broken tensor copy. That coherence is the practical proof that the OpenAI weights now sit inside our GPT model in the right places. Even a small loading mistake would usually break the output immediately, so this result is a strong sanity check. With pre-trained GPT-2 working, the model is ready for later fine-tuning tasks like classification and instruction following. The next task is to measure how the pre-trained model performs on the verdict dataset. That will turn the loading exercise into an evaluation exercise and show what the pre-trained weights know before any fine-tuning. The useful question now is not whether the model can generate text, but how well it predicts the dataset sequences. Comparing training and validation loss gives a quick look at how general the pre-trained model is on that data. Model size is the next variable worth testing. Larger GPT-2 variants should produce different continuations, and comparing them reveals how scale changes the quality of generated text. A direct comparison between the small and large models shows what extra parameters by you in practice. The prompt stays the same, so any difference in the output comes from the model size and its extra capacity. Token generation, decoding choices, training loss, and practical pre-training all fit together here. The goal is to understand how an LLM produces text and how we judge and improve that process. An LLM does not write a full sentence in one step. It predicts a single token, then uses that token to predict the next one. So the whole response is built sequentially. The model produces a probability distribution over the vocabulary, and greedy decoding chooses the token with the largest score every time. That makes the process deterministic, but it can also make the text less varied. Sampling introduces randomness, so the model can choose among several plausible tokens instead of always taking the top one. Temperature then sharpens or flattens the probabilities, which lets you trade off coherence against variety. During training, loss gives a numeric signal about how well the model fits the data it has seen. Validation loss tells you whether that improvement carries over to unseen text. So the two curves together reveal whether the model is learning well or starting to overfit. Pre-training is the stage where the model's weights are updated, so its predictions get better on the training corpus. Lower loss means the parameters are encoding more of the patterns in the text. The training loop uses familiar deep learning pieces, Cross-entropy measures prediction error, and AtomW updates the weights efficiently. Even though the model is large, the optimization setup follows the same basic pattern used in many neural networks. Training on a huge corpus takes a lot of compute and time, so using openly available weights is often the practical choice. That gives you a strong starting point without paying the full cost of pre-training the model yourself.